And today we're very happy to have Patrick Kidger, who is from the Mathematical Institute at the University of Oxford. He's a PhD candidate there working with Terry Lyons, and the subject will be neural controlled differential equations. And thank you very much, Patrick, for staying up late, and hopefully we'll ask interesting questions. Thank you.
Okay, well, amazing. Thank you very much for having me. Thank you for the invitation, and thank you for coming to listen. So yeah, I'm going to talk a little bit about neural controlled differential equations. As you can see, there's a subtitle there of a bit of a word soup. We're going to see quite a few different things along the way. So with that, let's get started. So I probably don't need to tell most of you, differential equations, obviously they're a thing. They've been a thing for centuries now, and we've been using them to model the world for quite a long time. And likewise, unless you've been living under a rock, then neural networks have recently become another way to model the world. And between the two of them, they're, I think, two of the most dominant modeling paradigms that you see out there. So I think what you do when you see two different concepts and you think both are cool, well, where you smush the two together and you hope something interesting pops out. And so I guess the interesting question at this point is this just some sort of awkward hybrid that was sort of dreamt up by a grad student running low on paper ideas? Or is it actually like, is this a genuinely really cool idea and a match made in heaven? And so my goal for today, by the end of this talk, is not just to tell you a bit about my own work and about neural controlled differential equations in particular, but I'm going to try and convince you that actually neural differential equations in general are an incredibly cool idea. The program for today, I'm going to begin with a little bit of an introduction to the general kind of concepts, the intuition and applications of neural differential equations broadly. And then I'm going to move on to discussing neural controlled differential equations, which is sort of my corner of the field. I'm going to discuss these in particular. And so we're going to see some intuition about how these are actually, they're actually quite familiar in many ways. They really look a lot like RNNs, and we can actually formalize that as continuous time RNNs. We're going to see how we can actually apply these to solve real world problems. You know, these aren't just like a theoretical toy. In particular, we're going to see some small bonus material on handling another kind of difficult data, namely long time series. At that point, I'm going to sort of apparently change tack for a little bit and start talking a little bit about neural stochastic differential equations. And the reason I'm going to do that is because it turns out you can actually train these as GANs, as generative adversarial networks, using neural CDEs in a really sort of like clever way, I think, or at least a cool way. And so this is going to be another application of neural controlled differential equations, again, to sort of solve, I think, a really interesting problem. And then just at the end, I'm very briefly going to touch on the software, so sort of convince you that we can actually use these things in practice. So with that, let's get started with the first section. So what is a neural differential equation and why you might already be using them? To just read off the slide, these are differential equations for which the vector field is parameterized as a neural network. So the canonical example here is really the neural ordinary differential equation. And when I have this little, can you see my cursor, by the way?
Yes.
You can, amazing. So when over here on the right-hand side, then we have a vector field, of course, and then this little subscript theta is just going to represent the fact that this f theta is a neural network with some vector of weights theta. And this f theta, this could be feed-forward convolutional, any of the sort of standard network architectures that you see floating around. And I think pretty much throughout this talk, anytime you see a neural network, it's actually just going to be a simple feed-forward neural network, maybe like 2 or 3 layers, value activation, something like that. It turns out that these are actually sufficient for like huge numbers of problems that neural differential equations actually get applied to. And more than that, it's still kind of an open question how to do even better than that. So just think of these as feed-forward networks. But as you can see here, we've got this initial value problem. And we started with something and just solve it forward with a neural network as our vector field. So the main idea for neural differential equations is that there's...
Can I ask a quick question? This is Yunjong
yes,
from
go for
Iran.
it. Sure thing.
Yeah, in your previous slide, you introduced the ODE like this. So I'm assuming that if the f theta is some sort of like neural network with the smooth activation function, we can guarantee some existence of the solution by utilizing this well-known theorem. But I'm wondering what kind of solution or existence are you assuming if the neural network, especially like, for example, ReLU network case, because we have one discontinuity so that we cannot yeah, so existence is somewhat tricky or to deal with, so that
it shouldn't be tricky. If you have a value network, then your network is Lipschitz, and at that point, your right-hand side is Lipschitz, and therefore, by standard theorems, you get existence and uniqueness, because you only really need Lipschitz in a pure vector field. Does that sound okay?
But do we need some, Lipschitz is fine for one variable, but we need a continuity assumption on the other variable as well.
So you mean with respect to both t and y? Yeah, we're assuming Lipschitzicity in both variables.
And the continuity as well, right?
Well, Lipschitz continuous implies continuous, so yes.
Okay, yeah, sure. Okay, I see. Thank you.
Okay.
Just a quick question. My memories on differential equations are kind of hazy. I used to teach that, but that was 10 years ago. You need just Lipschitz, or I thought it was something about the derivative being continuous.
I don't think so. I think you just need the vector field to be Lipschitz, basically.
Okay. All right.
Yeah, I agree with that.
Okay. All right.
Okay. So moving on then. So the main idea here is then that we're going to use this differential equation as a component of a learnt differentiable computation graph. And when I say this, these are the sorts of computation graphs that are absolutely ubiquitous throughout deep learning. Deep learning is the building of computation graphs. That's what makes it deep, right? And basically, instead of having a linear layer or a value activation layer or anything like this, then we're going to say, let's use a differential equation as a layer within our neural network. And indeed, this is exactly what you end up with. Of course, you see all these sorts of, sort of box and line diagrams all over deep learning papers. And this is the box and line diagram for just a simple ODE, a neural ODE, where here you can see we've got some input, whatever that may be, some input, so some vector in Euclidean space. Then we're going to use that as the initial condition on our ordinary differential equation, that we solve it forward in time. We get to some terminal time, capital T, and then our ODE solve. This is going to spit out this terminal value. Then we push it through a linear layer, and then maybe we actually stick a softmax in here as well, and we get some sort of vector of probabilities. That would be a simple example. So for example, maybe the input is a picture, and the output is the probability that the picture is of a cat. So if you've ever gone and done some sort of simple convolutional network, train it on MNIST, these kind of things, it's entirely analogous to that, right? Pictures go in, probabilities come out. You train from one end to the other using stochastic gradient descent. And so in particular, differentiating through an ODE solve, this is very straightforward, because an ODE solve is just our bunch of additions and multiplications, really. And obviously all of those are differentiable, so their composition as a solve is differentiable. If you're familiar with the field, you may have heard of something called the adjoint method. This is a way to actually treat this whole ODE solve as a differentiable primitive. But I'm largely not going to be discussing that today. But you can totally fit that in if you're interested. So overall, what we've got here, we've got some neural network. That's our little f theta here inside. This is a neural network. We've stuck that inside a differential equation. That's this whole ODE solve. And then we've stuck that inside a larger neural network that is this whole computation graph with boxes and lines. And the reason I think these are so natural and that this isn't just like a weird one thing inside another is that it's entirely a generalization of what we already do. So I'm told that many of you come from a sort of mathematical modeling background or something of that nature, and in which case a model of this nature is probably your bread and butter, where it's some differential equation and it's parameterized. And in this case, I really describe this as a neural differential equation because you're doing the same things. And so what I've actually written down here for as our example is what's called the SIR model. So this is a very topical choice, actually, because this is used to model the spread of a disease within a population. And so in this model, we've got 3 different scalar values. And so we've got S representing the susceptible portion of a population, I, the infected portion of a population, and R, the removed, that is to say, recovered or deceased portion of a population from a disease. And then you can see, we've sort of sat down, we've thought a little bit, and we've said this thing over here on the right-hand side, this is a vector field that describes the dynamics of this system. But it's not completely specified because we've got these 2 parameters, B and K. And so there's this parameter B, which controls the infectivity of the disease, and there's this parameter K, which controls the removal rate of the disease. And what we're going to do, the way we sort of actually use this sort of model in practice, is that these are parameters that are learned from data. What we do is, we've got our model, we've got these parameters, but now we look out into the world, we observe some disease, we gather some data, and then we fit the model to the data. And we do so by choosing these parameters very carefully. And when you think about it, this right-hand side is a neural network. It's a neural network with a very particular form, and it's the form I've just put on screen now. You've got some inputs, that's the yes and the I. You've got some parameters, that's these parameters B and K. We push it through this particular collection of operations you see in the middle, and then this spits out the outputs. That spits out the vector field that we're going to be using, the way in which these values evolve. And so because of this, not only am I saying that this thing on the right-hand side looks like a neural network because it's got all these parameters and things, but actually we can train it in the same way. If you want to fit an SIR model's data, then one perfectly sensible way of doing this is actually just by gradient descent, by the stochastic gradient descent I introduced earlier, in the sense that you write down some loss between model and data, and then you minimize this thing. I think what I'm really trying to say is that neural differential equations are not a new concept. They're a very old concept. We've been doing them for a very long time. And it's just that general neural networks, like feed-forward neural networks, are just like the next step along this chain of what we're already doing. And so just to sort of hammer this point home, here's another example. So this is an example from mathematical finance now used to model asset prices. And so you can see here that it doesn't have to be an ODE. Here we've got an SDE. And this is an SDE with, again, it's got some very particular structure, which is motivated by thinking about this from first principles. But we still have these parameters. We've got these parameters mu, kappa, theta, and psi. And the way we fit those is that we look out into the world, we gather data, and then we pick parameters which do a good job of making this model fit the data. So this is really still the same story. That's from the mathematical side. So if you do mathematical modeling, then hopefully that's convinced you this is a reasonable thing to consider. If you're coming from a machine learning background, then maybe mathematical modeling isn't what you do, but you're familiar with things like residual networks. And in that case, if you take this ordinary differential equation that I've already written down, and then you solve it using the explicit Euler method, just a very simple numerical method for solving ODEs, then in fact you end up with this. And this is now precisely the formulation of a residual network. If you like, you can absorb that delta t into the F. So what you see here, and in fact historically, actually, this is seems to be one of the main reasons that neural differential equations became a thing, is because someone spotted that, oh, hey, these two things look very, very similar, and that the things we've been doing for centuries with differential equations actually look an awful lot like these things that we're now using in machine learning. Okay, so that's broadly speaking the end of my intuition, and hopefully, as I say, that's convinced you this is worthwhile. So in terms of the applications that we're going to that neural differential equations see, to my knowledge, there's 3 of them. There's all of the things which are already using differential equations. So this is all of the stuff that you see in like your textbooks, where you've got physical modeling, biological modeling, financial modeling, all this kind of stuff, where we're already using differential equations. And so one of the totally sensible things to do is to go and take whatever model you're already using and then find some way of enhancing it with a neural network. And there's a bunch of different ways you can do this. But this is sort of one sort of natural way of doing it, especially if you're coming from mathematical modeling. Another one is with respect to generative modeling. There's a class of neural differential equations called continuous normalizing flows. I'm not going to be discussing them here today, but if generative modeling is your thing, then neural differential equations are of interest. But then finally, the third one, and really the one we're going to be talking about today, is time series. And this is because ubiquitously in time series, more so than in any other domain, time series data is messy. It can be irregularly sampled, it can be partially observed. The missing rate of the data can be informative. The data can be variable length, it can be incredibly long. All of these things make it complicated to work with. And neural differential equations have, at least I think they have the answer. This is the one we're going to be talking about today. So that's the end of my introduction. I'm going to start talking about neural controlled differential equations next. So I just want to very briefly pause and ask if everything sort of mostly seems clear, or if there's any questions so far.
Can I comment on one thing in your previous slide?
Sure thing.
So I think there are people who attempt to understanding the effect of depth in the continuous level. They also use the neural differential equation. And if you go back to one more slide you introduced in terms of the ResNet, then actually you can interpret the time as in the discrete level, this subscript n represents the depth of the layer.
Yes.
So yeah, just the one comment on that.
Yeah, I agree. I've not really been talking, so I suppose in many ways, when I say applications, I mean sort of applications for the applied mathematician. And you're right, I think there's a lot of actually very cool theory here. It's a personal theory, not completely founded on evidence, but it's a personal theory that actually huge amounts of the successes of machine learning, of deep learning, are actually based on differential equations, and that somewhere, for example, here, there's like a perhaps hidden differential equation structure, which explains why it works, which is indeed definitely of interest to the theoreticians.
Patrick, can I make a comment? Appreciate the pedagogical style, but most of us here are doing this for a living, so you can be a little more advanced.
Okay, sure thing. Sure thing.
Feel free to intrigue us more.
Okay, no comment. No problem. I mean, let's do that. So in that case, neural controlled differential equations. Let's get going into the real meat of this. So we're going to consider the neural ODE. So this is the neural ODE I've already written down, but not in differential equation form now, but in integral form. And this integral that I've introduced, this is introduced and then integrated over. It's just some internal detail of the model. In the language of software development, it's an implementation detail. We don't see it from the outside. But if in fact we have some ordered data, so here we've got some sequence, maybe it's a time series, then what we would like to do is align this introduced dimension with the ordering of the data. That's kind of our motivation going into this. But the problem is that it's an ODE. Because it's an ODE, the solution is determined by its initial condition. And there isn't like an easy way to kind of fit in this extra information. Maybe our initial condition is a function of x naught, but there's no real way to fit in functions of x1 and xn. There's no way to input them into the model. Well, that's what I've just said. So the solution to this is perhaps hinted by the title. This is these neural controlled differential equations. So if we just cross out the word neural for a bit, because I appreciate that controlled differential equations are actually not super well known. The basic idea, and by the way, I should make this clear, by the way, going in, this is different from control theory. We'll touch on the difference in a little bit. But the basic idea is that we're going to have the local dynamics of the system depend upon this time varying path. And then what we do is then we write down what we call a controlled differential equation. So you can see that we've replaced the ds with a dxs. And what we now have is, so this is what we call a Riemann-Stieltjes integral. And the right-hand side is a matrix vector product. So f is now matrix valued and x is vector valued, and we multiply the two together. If you're not familiar with Riemann-Stieltjes integrals, then for most purposes, I think for all the purposes I'm really going to be looking at today, then you can actually interpret it as an ordinary differential equation in the following way. So this can be interpreted as a familiar looking object. So why is this natural? Why would I consider writing this down? Well, first of all, changes in x provoke changes in y. Changes in x create can be seen through y. So this gives a way to input data into a system, which is really what we're trying to do here. And in particular, they generalize equations of this form, because I think certainly if you were to ask me, how do I input data into my model as it evolves along, then probably this second equation is actually what I write down. But it actually turns out that this is genuinely a special case of the first one. And in particular, you can see this by taking the f constant equal to 1. That first controlled differential equation, you end up with just an integral dx, and the two things cancel out, and you just end up with y equals x. And so what you see here is something that's modeling the identity map from x to y. But actually, in this second one, yeah, go on.
Yeah, sorry, just a quick question. So your dxs is x prime ds, so that's not of the form that you wrote down, or I mean, depends what you mean by f, I guess. But it's the
yeah. If you wish, you can sort of write some other capital F, maybe, I don't know, that takes in these two things, both the little f and the x.
Yeah, but it's more like a functional that takes the function x and will return, for example, its derivative or something like that.
What is a functional specifically?
Well, I'm saying that, well, you see the generalized equations of this form.
Mm-hmm.
So, I mean, it's x prime. I mean, it's not a function of x, right? So yeah, I'm not sure that the form here is really correct or helpful.
No. So this is part of why that first one is a generalization, because of the fact that we have an x prime in that first one and we don't have access to the derivative in the second one, then that's why we can model the identity in the first one. But in the second one, we are constrained to have integrals of x.
Sure.
The second one could be nonlinear in x, whereas the first.
Oh, certainly. It can certainly be nonlinear, but you're still losing something.
Okay. So it's not a proper generalization. Yeah, different.
Oh, no, it is a generalization because this first one, it's linear in dx, but that allows it to be nonlinear in x. So every equation of the second form can be described by an equation of the first form, suitably modifying f. And then, as sort of already been hinted on here, then CDEs offer a way to model nonlinear operators between paths. And to be slightly more specific, they offer a way to model operators which have some sort of notion of causality. Mathematically speaking, they respect the filtration, y respects the filtration of x is adapted to it. If you're interested in Googling this later, then this particular operation has a special name. It's called the Ito-Lines solution map. So why is this natural part 2? Then this has an integral form that can be, well, I suppose in some sense the first one is already an integral form, but we can write it now like this. And of course, this looks a lot like SDEs. And historically, this is really where controlled differential equations came from, out of a desire to understand SDEs better. And I think now, particularly now when you write it now in this form, it becomes a lot more obvious that you can sensibly compose these objects. So we've got y being driven by x, but now we can drive z by y, and of course dot, dot, dot as much as you like. You can keep doing this. And it just sort of becomes like a somewhat easier, slightly more natural thing to do. So that's the background on controlled differential equations. I'm now going to reinstate the word neural in front, and we're going to look at an application to irregular time series. And you can probably more or less guess roughly where this is going. So if we assume we observe some time series, and here it's a time series that is irregularly sampled, but completely observed. And the observation times are ti, and the observation values are xi. And the fact that it's irregularly sampled but fully observed is really just for kind of simplicity of presentation. And actually you can do things like partially observed and so on as well. And now what we're going to do is we're going to join up the dots. And we're going to join up the dots and we let capital X be this interpolation of the data such that it takes the appropriate values at the appropriate times. And at this point, by the way, if you have informative missingness, you don't have to lose it. You don't paper over that with the interpolation. That there's ways of fitting that in as well. And then what we're going to do, our goal is to learn some functions zeta, f, and L. So the first two are both neural networks. And we're going to learn it such that, as we said all along, what we really wanted to do was have our initial condition be a function of where we start, but that now we want a way to incorporate incoming information. And that's now exactly what this controlled differential equation does. And now because this f theta is a neural network, it's a neural controlled differential equation. And the output of the model is then done via this linear map, this L theta, on either the final y or on the time evolving y. And as I've said, zeta and f should be these arbitrary neural networks. And then I describe y as hidden state. So
Patrick, I have a question.
Yep, go for it.
Yes. So in other words, you start with x, right, at the level of the paths of x. Mm-hmm. And then you go and you using this formulation that you have there, you elevate it to this latent state, which is y, mm-hmm. right? And then you use this integral form to evolve y, and then mm-hmm. you come back through the linear transformation back. You can come back to the level, for example, that you had originally, right? Maybe you can come back to x.
If you wanted to, yes. I guess you could use it as an autoencoder.
Yes. So I suppose that at some point you will also give an example where you specify what is x and y, because now I see, I mean, I've read about this before and I understand the construction, but I would like also to see what it is at a specific example, maybe later.
Yes, yeah, we will see. We'll see an example in a little bit.
Okay, thank you.
And in fact, actually, we're gonna. Sorry, wrong direction. We're gonna start off with a small picture, actually, which I think helps make it clear. Which is, we've got some process x, we have times t, we make observations xi, we join at the dots to create capital X, and then in continuous time that drives y. And this is kind of the picture to have in your mind. And the reason, in particular, I think this is kind of important. The reason there's this extra L in there, and that we're doing this linear map on y, can be seen by looking at the RNN, a sort of analogous RNN, because what we've got here is really completely analogous to an RNN, where in discrete time we've got updates xn we've got input xn updating the y, and as you go along, this updates your hidden state y. And of course, if you're doing an RNN, then you don't expect the output of your RNN, so the hidden state of your RNN, rather, to be your output as well. Usually you have your hidden state and then you have a map from that to the output. So sort of from an ML point of view, that's kind of why you want this hidden state y. And slightly more specifically, if you don't, then, and your y was just your output, then you would have some sort of Markov property, which in general isn't desirable. And so, go on.
This is Leo. Just a quick question to make sure I'm understanding correctly. So basically, now, I mean, in this form, the proposed form is basically like, say, the updated y is f theta of y product the updated of x, right? I mean,
yes.
the yn plus 1 minus yn, right?
I'm sorry, I didn't catch a question in that.
Oh, no. So I was asking, try to ask you, my understanding correct, is that like in your form is basically say like yn plus 1 minus yn is f theta yn product xn plus 1 minus xn.
Sorry, are you saying what would happen if we discretize this controlled differential equation and the fact you'd end up with something slightly different? Yes, that's correct. My theses here are slightly different from each other.
Of course.
But despite that, actually, for any RNN, you can actually write down, I'm not going to do so, but you can write down a neural CDE, which it is the discretization of. And this is why I really meaningfully describe CDEs as neural CDEs as being the continuous time limit of an RNN.
Okay, makes sense. Yeah, thank you.
And so I think throughout my whole presentation, this slide more than any other is really my most important one. And this is the one that sort of puts, I think, most of the key ideas to fix in your mind on one page. Okay, so as I say, we call this a neural controlled differential equation. And indeed, here we see some examples. And so the example here is that we're going to have this time series. This could be the position as a pen is moved over paper. And so just be unambiguous here, this xy this x is different to this x up here. So this could be the position as a pen, it's moved over paper. So we're drawing the letter A, the letter B, the letter C or something. And maybe our end goal is to classify the character, in which case what we'd probably do is we'd go for this first form here, this L theta, where we have a map on the final YTN to perform classification. Or alternatively, this could be patient hospital records. Did someone speak? Doesn't seem like it. Okay, so yeah, so another example is patient hospital records. So this is, I mean, you've probably already read it by now, heart rate lab results and so on. And medical data is a really classic example of messy, irregular data where things just aren't nice. And this is, I think, sort of one of like the key applications to have in mind is messy data, because when we've got messy data, the fact we've got this continuous time formalism really helps make things work. This could be things like spoken audio, it could be weather data, and indeed it can also be physics, the movement of some physical system. And I think actually this is quite an important point to sort of emphasize, because you look at a lot of classic examples of mathematical modeling, the sorts of things you'd probably sort of study an undergraduate like fluid dynamics or something. It's very often these sorts of systems we can hope to write down and derive a theory for, and very often that is physics or finance or something. And in many ways, what we're seeing here is that we don't have to constrain ourselves to that, and that we can very meaningfully and with great benefit use differential equations as a way of modeling things like medical data. And I think that's just the sort of application that you just don't normally see whenever you talk about differential equations. So I think that's kind of cool as an idea. So the advantages of using neural controlled differential equations just at all is, well, first of all, the most important one, I think, is that it's a continuous time theory. And as a result, this makes messy data really easy to handle, because interpolation, messy data, no problem. We can just do that. And the messy data doesn't have to affect your model. And what we've done is we've introduced this abstraction of this capital X, this continuous time path between our data and our model. Yeah, again, in the language of software development, we refer to this as maybe an interface. Next up, this equation, this is a neural CDE, but now you can see I've deliberately written it and interpreted it as a neural ODE. And the reason why I'm doing that is because we could, we have software for ODEs, we have software for neural ODEs, and we can just push this through and it just works. So this is a really easy thing to actually use and actually get started with. And moreover, I mentioned the adjoint method very briefly earlier, and I'm not going to try and explain what this is in too much detail now, but if you're familiar, then this, again, totally carries over, and you can get great large memory savings as a result. And we'll see a numerical comparison as a result of that later.
Excuse me.
Go for it.
So you're saying that you can use existing software. So if I have observations, right, at x0, x1, xn, and then you do the interpolation, then you get this capital X, right, which is it does not have these gaps that you had the discrete. But if your data come at irregular times, if you use this continuous time function, which is capital X, and you compute this derivative, dx ds, this derivative will not be very accurate, right? So all I'm saying is that you can you can use existing software to solve that equation, but I don't know how accurate will be the quantities that you enter there by using this dx ds, which is an analytically computed derivative of something that started as a discrete and, like you say, messy time series.
So the answer there is that it doesn't need to be accurate.
Okay.
When we write down this capital X, the intuition is that it's somehow approximating the underlying thing that we sampled to get our data. But in terms of like how we actually use this, it does not need to do that. It just needs to be some principle. Specifically, needs to be an injective map from data into path space. And as long as it does that, then actually I don't care.
Okay, but all I'm saying is that if you have big gaps between observing your time series, this must show up somewhere at some point, right?
Sure.
Yeah, so you're saying that you don't care, that as long as you have an injective map that takes you to path space, but this map, it carries the information that was on the sample data. And if that information comes at a sparse instance, there isn't much information there, right? So you're just saying that whatever information you have, you will just use it.
I mean, yes, I guess.
Yes.
I'm not sure what your point is. I certainly can't magic more data into existence. So
let me ask a kind of a related question. So if, for example, you sample X differently, are you going to get a different model, or how do you converge in terms of being insensitive to the location of the measurements?
Depends whether or not you want to be insensitive to the location of the measurements. Typically, you don't. Typically, the when the measurements were made actually carries information as well as what those measurements were. And the short version is that you can actually construct X which either do or do not carry the sampling information within them.
I think I understand that whatever information you have, this is a way to introduce it into
Yes, essentially.
I see. It's a way to incorporate the information. So whatever accuracy this information comes with, it doesn't matter, right? It's just some information, and this is a way to incorporate it.
Yes, that's exactly it.
Yeah, but let's say we take your medical example. So you have a set of measurements, medical data, and so on. You build your model. Then you want to make a prediction. So you get a new set of measurements, new X's. So how do you guarantee the accuracy of your model with respect to these new measurements that may very well have been taken at different times, like different time intervals between X's?
I don't see why that's a problem. My training data, so to be clear, my training data doesn't always have the same timestamps. Right? My training data will consist hopefully of the same messy data that you're going to use at test time as well.
So for example, let's assume for the sake of argument that you just have two, you have one set of medical measurements, and you just for the sake of argument, you subsample, do a training, and then you sample differently, do a testing. The accuracy on the testing could be widely off.
So if you were using different sampling strategies between train and test, then yeah, I believe things might go wrong. But that's a story throughout machine learning, right? If you test on something you didn't train on, well, yeah, obviously, things don't work out as well as you'd like.
So in other words, you train using some sampling, right? By training, I mean, you learn the parameters for theta, right? And then if I come to you with a different time series, which will give me a different dx ds, I just use it as an input, but with this trained network, right?
Yeah.
So whether it will be an accurate prediction or not, like you said, it depends, right?
Well, the way I understand, you need to have the same time sequence as for your measurements for this to work.
I think the way that it is done, that it's elevated into continuous time, you don't necessarily need to sample them at the same time, but when it comes to the accuracy of the prediction, that's a different question.
So recall that we're not just training this on like just one sample, right? We have some large corpus of data, some thousands of hopefully of samples at least.
Yes.
And each of these will have different measurements, different times. It's not like every sample in my training corpus was measured at time 0, 1, 5, and 10, and every one in my test corpus is measured at 1, 3, 7, and 9. Like my training corpus has lots of different time measurements, and there's different timestamps, and those timestamps will be different between different observations for different examples from my data set. And so the model, when trained, sees lots of different kinds of time sampling strategies. And then when it tests set one of these lives, then hopefully it's seen one in the training set before.
Right. So that was the answer to my question. So basically, you are saying that the training set has many different sampling strategies, and therefore, my example with the testing, it would work because you simply would have seen similar sampling, hopefully during the training.
Yes, exactly. Yeah, I'm not. This isn't a way to try and somehow fix or work around different sampling strategies. Like if you want to do that, then yeah, by all means, try and come up with some solution that fixes that.
Some related question upon this, so that I think that all comes down to how you interpolate data. So how you construct X, because there are multiple ways you can construct, interpolate the data, so that depending on which construction you are using, I think that also, so that another way of, I think the Panos and Eric asking is something like, depending on which approximation method you are using it, then how does it affect to your final result?
So you can write down a bunch of theoretical conditions that your interpolation should satisfy. And basically, like at least in theory, as long as you satisfy those conditions, then you're good to go. And the main one here is something like injectivity, where you're saying that, by taking your interpolation, you're not throwing any information away.
Okay, so then in your case, then what is your construction? What method are you using for constructing X?
So the easy choice is often natural cubic splines. These have certain issues like not being causal, and yes, you can go in and you can fix those, but natural cubic splines turn out to be a good choice actually for computational reasons. These turn out to be things that you can solve this integral with numerical differential equation solvers particularly efficiently.
I see. Thank you.
Guys, can I make a suggestion? Can I respectfully request that we let Patrick finish? Because I think maybe if we can see some of his results and stop guessing what they're going to be, we might be able to get through it faster.
Well, we have 20 minutes and I have another 30 odd slides. So yes, we need to get going. So thank you. And so I'll try and move a little bit faster. The existing theory of CDEs is quite a well-developed one. And I think whilst you sort of don't need to know it to actually use these models, and I think develop a lot of these models sort of like for deep learning applications, it is of great interest if you want theoretical guarantees. And so in particular, you can show that these things are universal approximators, which is quite a nice thing to have. And then additionally, these are nil CDs demonstrate state-of-the-art performance on time series problems, which is, I think, probably the thing that the deep learning people like to hear. And so on that note, let's back it up with some numbers. Here is an example. So this is actually the very first example I gave on the time series, the example of time series slides a couple slides ago. This is a data set of handwritten digits, people writing the letter A, the letter B, the letter C, and so on. And the job is to try and classify which of these digits has been drawn based on the XY position of the pen on the paper as it changes over time. And so in this particular example, we compare nil CDs against a bunch of other different models, sort of broadly from the same class. And we see this, the story I think that you see claimed in every machine learning paper, which is that our model does the best. And in this case, we see that we outperform the other models considered. And actually, because of this adjoint method that I keep sort of alluding to but never really explaining, we actually do so using an order of magnitude less memory. And then I could talk a little bit about how much data we're dropping, but I think in the interest of time, I'll skip over that. So I compared this to control theory earlier. I'm guessing this is a topic that some of you may be familiar with. Speaking very broadly, like a huge generalization, there is a certain difference between control theory and controlled differential equations, which historically developed separately. And that is that in control theory, the system F, this is usually fixed, and the goal is to try and find some optimal input, some optimal path X that produces our desired response. But with neural controlled differential equations, this is flipped around. The input is fixed, that's the data that's given to us, and now we're going to try and train to find some optimal system F that produces our desired response Y. And essentially that's the difference between them, because these two things actually do still have an awful lot in common, and I'm not going to tell you otherwise. So I think in the interest of time, I'm going to skip over the bonus material, which is long time series, but it turns out that you can use neural CDs for long time series as well. And I think you've all got the slides, so you can maybe have a look at that as well if you're interested. So neural controlled differential equations, that's the central ideas, I guess I would say. And perhaps at the risk of spending another 10 minutes talking about it, do we have any questions at this point before I move on to discussing a slightly more complicated application to SDEs?
Well, I do have a question, but can we ask, or do we want? I mean, I'm okay with moving on. I don't want
as
to
long as it's very brief.
So okay, I'll keep it for later.
Eric, go ahead. I mean, the idea here is not to keep it an hour. Patrick, go on. If people ask questions, keep going. Finish your slides. Those who want to drop off, they can drop off. I rule. I will overrule here. So everybody, please ask questions. Make it interactive, and then if it's an hour and a half, it's an hour and a half.
Sure thing. Okay, in that case, let's crack on. Neural SDEs, here we come.
So no, Eric can ask his question.
oh, sorry, I misunderstood you. In that case, do go ahead.
No. I said we ask questions. I overrule Nat.
Okay, so yeah, my question is as follows: that so actually now I understand a little bit better what you were alluding to previously with your equation. What was it? F of y comma x. So and so yeah, can you describe a little bit the difference between your CDE and kind of assuming more? Actually, I don't know. I understand. Actually, you said generalizes, but I would view your approach as sort of being simpler, because you assume that the dependency on x is just through dx ds, just the derivative, and you could also just train a neural network which takes as inputs, say, y and x prime, or y x and x prime, or something along those lines. And of course, this is a more general form, probably harder to train, and so on and so forth. But so the question is, is there a gain in accuracy, or what are the trade-off between the form you're assuming, like basically this dx, versus a more general, let's say, f of y, let's say x prime ds, for example?
Yeah, okay. So if you have some sort of nonlinear dependence through dx, then yes, that is obviously more general than what I've written down up here at the top. But what you can say is that a linear dependence on dx is strictly more general than a nonlinear dependence on x. And the basic idea is that it's possible to record x into some extra state and then replay that state through your y.
I understand that, but
in a
basically,
nonlinear fashion.
How about you make your function f of y and x prime, for example?
I mean, you could do that, and I'm not, I'm not going to stop you from doing so if you really wish. The same basic idea of let's get some input in is really the most important part here.
No, but it sounds that your presentation kind of hinges on the fact that the form dx is preferred for some reason.
So
but I'm not saying you're wrong. I mean, it seems that this is perfectly valid. You have your linear in dx ds, and it's a simple form, and it's easier to train, and you probably have some robustness and accuracy and stability, because of this. But it does, since you have a neural network, you can sort of input whatever you want. So you could input, y and x prime, and so that's why, I was curious.
Yeah.
But anyways, I mean, if you haven't tried that or compared that, that's fine. Yeah.
The simple version is no, we haven't tried that. I think you could. I suspect, broadly speaking, it's all going to work out kind of the same regardless. What I can tell you we have compared against is actually the two equations you see on screen at the moment, this dx versus the inputting x directly. If I jump forward to the table I had.
Yeah, but the problem is you're looking at x instead of dx ds, so it's not really the same thing.
Oh God,
I mean, it's only partially answering my question, let's say.
In that case, what specifically would you?
Well, you have x prime instead of x.
If you want a nonlinear dependence on x prime, then yeah, by all means do so.
Right.
And if you like, you can view this as a CD with respect to the second, d dx almost, d dx dt.
That's right. Yeah, yeah.
So you can certainly, you can push this to as many derivatives as you really care for. Whether or not that's actually going to give you anything in practice, and I don't know, I've not tried it. I think certainly you're going to hit diminishing returns at some point.
So here, the model that depends on x, which one is it? It's the D1?
That's the worst one, actually, at the very top.
Oh, the
that's
GRU
the
OD.
GRU at the very top.
So it's a function of y and x.
Yes, exactly. We see that one actually does the worst. And we speculate, but don't know so, but we speculate it's actually because of this theoretical gap. It also might not be. It might be for any other reason, but there is clearly something there.
Yeah, because I would say the derivative x prime is meaningful, but the value x itself, less so. Anyways, yeah, thanks. Thank you for your answer. Yeah. Okay, thanks.
No problem. Okay, so in that case, neural SDEs. So,
excuse me.
Oh, hello.
So this is Lulu. I have one question. So if X is high dimension, then how should we do the interpolation?
You consider each channel separately, loosely speaking. There's some sort of asterisk attached to that. But basically, you consider each channel separately and just join up the dots.
I mean, for each component, we do interpolation separately, or then can we guarantee the accuracy because in high dimension, then everything becomes sparse. If we do this brute force way, then I'm not sure what's the accuracy.
So if you're saying you've got some incredibly sparse data in high dimensions, and maybe you somehow want to use values in other dimensions to help you do your interpolations in the ones which have missing data, then yeah, like that's totally valid. The reason I just say interpolate is because broadly speaking, that's all you need. And by all means, pick an interpolation that's adapted to the problem at hand.
Okay, thank you.
Cool. Neural SDEs? I'll take that as a yes. Okay, so neural SDEs. We're going to be seeing these as in terms of GANs. So I'm going to give a quick one slide overview of GANs, sort of emphasizing the points that we really are going to need. And so the idea of a GAN is that we want to approximate a random variable, some distribution and some probability distribution. And we're going to assume that we have access to some source of noise. So typically this is just some normal distribution, some multivariate normal distribution. And then we're going to try and learn a neural network that maps from one to the other. And so I'm just very informally here saying that I would like these two distributions to be, so these two quantities, sorry, to be approximately equal in distribution. Well, I've taken my noise and pushed it through a neural network, and I want samples from that to look like they've come from A. And the key, sort of the three key points here, these aren't unique to, well, some of them you see in other generative models, but the sort of three key points that between them a GAN are kind of defined by is that it's a map from random noise that we can sample from, but that in particular, we cannot write down a probability density for. So it's a map from random noise by definition. We can sample from it by just sampling some random noise, some B, and then pushing it through our neural network and seeing what pops out. But we can't write down a probability density for it because whilst like theoretically I can certainly sort of write down G theta inverse, blah, 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 blah. It's a neural network, and inverting it is a terribly complicated sort of thing to do. So we can't expect to be able to evaluate this thing at least. And so the way we're going to train a GAN then is that we have these scalar statistics, which we call a discriminator. And what we ask is that this statistic of the learned distribution should be as far from the true distribution as possible. Our scalar statistic tries to push these things it tries to identify the way in which these two distributions are most different. Because in doing so, that then tells the generator, the G theta, it then tells the G theta how to get better. So this is how I'm going to be thinking of GANs. And if you're already familiar, then of course this is all very straightforward. But the point I put in bold here, that these three properties are the three I really want you to fix in your mind, because these are the three that we're gonna see pop up again in a second. So SDEs. Pause, put the GANs on hold briefly. Just okay, the same sort of recap for SDEs. Here I've got some SDE. I've got some X0, which is sampled from some initial distribution nu, and this thing we're going to get some X, which is some vector valued path, with driven by some vector valued Brownian motion, And correspondingly, we have some drift mu that's vector valued and some sigma that is matrix valued. And so on the right-hand side, we have a matrix vector product between sigma and dw. And then in some sense, so the question of what does it mean to solve an SDE? Because of course you open a textbook and you see strong solutions, you see weak solutions, you see several different equivalent definitions of the above. And there's one in particular, which is like really, really important to where we're going with this. And this is that the strong solution of an SDE is the unique function that maps from noise to the thing that solves this integral equation. So you can see it's this unique function f, which takes in the initial probability distribution. It takes in the W, our Brownian noise, our source of noise over time. And we're going to ask that this thing should actually solve this SDE. That's a strong solution to an SDE. And hopefully, as I'm saying this at this point, alarm bells are going off because it's a function of noise. Well, that's actually this point A here that we mentioned earlier. And so we say that this solution to an SDE, well, it's this random variable on path space, each sample is a path. And as I say, it's this function of random noise. We can approximately sample from it because that's what SDE solvers do. Random noise goes in, SDE samples come out. And there's no natural notion of probability density. And actually, in fact, because we're working in infinite dimensions in path space, the usual notion of probability density doesn't even exist. It's not even defined. You can kind of make it work in a few different ways, but it's not the same concept you're normally familiar with. So what we end up seeing here is that these 3 points are, of course, exactly what I mentioned as about GANs earlier. And we see that an SDE precisely fits the intuition, precisely fits what we do with GANs. And so I think it's this kind of deep convergence where what we've seen in mathematics for quite a long time now, and what we've seen in machine learning for quite a long time now, these two things actually come together. And so how are we going to end up using this? Well, we're going to say, okay, let's go. What would I say when we're using a GAN? We're going to try and model a random variable. And because it's an SDE, it's a random variable on path space. And we're going to have our noise, we're going to have our input noise. This is going to be some Brownian motion, and it's going to be some initial noise as well. And then we're going to learn a collection of neural networks. And then again, this is going to have this linear readout map that is kind of ubiquitous at this point. And then we're going to try and learn an SDE of this form. So you can see that over on the left-hand side, we've got some x0. So this is now some function of our initial noise. And then we've got this general SDE over here in the middle. This is just anything that you really want to put in here for these neural networks. So in principle, this could in principle learn any SDE. And then once again, over here on the final part over here, we've got some linear readout. And our goal is going to be that this Y is now going to be, again, very informally in some sense, approximately equal in distribution to this target random variable that we're interested in. And so this target random variable is going to be something that we have samples of. So maybe it's samples from the stock market, which of course is, this is some sort of discrete tick data that we lift into path space in some reasonable fashion. An interpolation scheme, as we've already seen, for example, would suffice.
So Patrick, quick question. So in this setup, this dw now plays the role that dx played in the previous deterministic setup?
Very similarly so, yes.
Okay. So that's the driving. Is this the one that's considered driving the evolution? Okay. All right.
And so I think historically, DW, Brownian motion drivers, were considered long before sort of general DXs were considered.
Right.
But if you wish, you can, well, I guess if you've had any background in SDEs, then this is probably looking a lot more familiar than the controlled differential equations I introduced earlier.
Right.
But actually, if you like, you can interpret an SDE as a controlled differential equation.
Okay.
And this is where controlled differential equations come from historically.
All right. Thank you.
Excellent. And so I think I want to give you just sort of like a quick moment to stare at this and sort of justify some of the choices that are being made here, because you can probably believe that this is a sensible thing to do, but why just this, and why can't we simplify this? And so I think the points to highlight are that we've got some function here of initial noise. And the reason for that is because our other source of noise, our Brownian motion, is only going to affect the evolution. It doesn't allow us to choose where we start. And so this x0 equals a function of initial noise is kind of all on its own, is kind of like a mini GAN problem. Just this on its own is trying to match the initial distribution. And then X is then representing hidden state. And this is now completely analogous to the CDE we saw earlier, that we need hidden state if we don't want to be Markovian, which in general we don't. And this is why we then have this extra Y that is then this linear readout on what we've got. And if you really want to, by the way, you can totally fold the cell into the drift, and you can sort of make things work there. But I think this is the clearest presentation. So I've told you that this is an SDE, and hopefully this looks a lot like the generators of a GAN that we've been describing. But the outputs of a model are continuous time paths. Why? This is what we get when we sample an SDE, and we need a discriminator that accepts such objects as inputs. And you might be able to guess where this is going, because we have seen such objects before. And so at this point, if I just get out my red pen and just scribble out all that stuff to do with time series, and then I can just update my notation slightly, then you can see that actually the CDs that we've already seen, these are objects which take in continuous time paths as inputs, and therefore they are suitable objects to use as the discriminator of a GAN. And so now if I put my red pen away and try and sort of write this down a little bit more formally, then this is it in sort of full gory detail, which I'm not expecting people to sort of pass every exact detail of this right this second. But there's sort of the quick summary. So we've got input noise going to generator. Generator is an SDE. This evolves forward in time. It has some output. And then you can see that this Y that is an output of the generator is then used as the driving input of the discriminator, which is a neural CDE. And then when we get to the very end, this hidden state that's at the very end of our neural CDE, the terminal hidden state, we're then going to map that down to some D, and that D is going to be our score. This is the real versus fake score that GANs, that a discriminator in a GAN does, that it has. This is what it calculates. And so SDs and CDs together form a generator discriminator pair. And arbitrary different diffusions that inside this generated arbitrary different diffusions are admissible, so that in the infinite data limit, any SDE can be learned. So in principle, given enough data and enough training time, then we can match any underlying SDE distribution. And so I think at this point, what's actually kind of nice is to sort of look back at the kind of the introduction to this talk when I was talking about kind of neural differential equations in the abstract. And I said, oh, well, these sorts of things have been around before. And I introduced the Heston model as a simple example. And so I think what's quite nice is to appreciate that now, this was a neural differential equation very meaningfully. And now this is the generalization of something like the Heston model. And now we can learn any SDE. Okay. So I say that we can do this, and we can. And once again, this is a big table of results, which is hopefully convincing and backs up my arguments in that we compare SDEs to a bunch of other sort of similar models. And we do so on a few data sets where, like, I'm not going to try and convince you that SDEs are fit for every purpose, because of course, SDEs are models that we use in certain contexts because we expect them to be good models. And so classic examples of this are something like stocks. Of course, this is how the finance industry is making lots of money, is by modeling things with SDEs. And so it's perhaps not a huge surprise that neural SDEs actually turn out to be a really great fit for stocks data. And this is actually a data set of Google stocks. I think over the course of a year, 2 years, split down into something like 1 minute increments. And then we've got a couple other data sets, and then once again we sort of see the same sort of story, that neural SDEs are a good fit for many different data sets. Okay, so I'm getting towards the end of my talk, which is just as well, because we're running out of time. So I'm just going to spend a brief moment just to talk about the software for these sorts of things, because I think it's one thing to write down the theory of this and to appreciate that somehow this works. But at the end of the day, we need to push this through our computer and actually do this. And the good news is that actually, we've got software for this, and it's very straightforward. And so particularly if you're a PyTorch user, then there's TorchDiffEq for ODEs, there's TorchCD for controlled differential equations, and there's TorchSD for stochastic differential equations. And meanwhile, if you're a Julia user, then there's the reasonably comprehensive differential equations.jl. And these fit into their ecosystems. They're auto-differentiable, they're GPU capable. We can compose them with whatever else you want to do inside this differentiable system. Maybe this is just some smaller part of a larger pipeline, and you can make that work. I think I've got a slide at the very end with some references for these if you're interested in looking these up. Of course, you can also Google them. Yeah, there we go. So that really does bring me to the end of my talk. So I guess the summary is that neural CDEs are a new tool for time series that bring together the well-understood mathematics of CDEs with the well-understood machine learning of neural ODEs. They act on messy, irregular time series, and whilst I skipped over it, they can also act on long time series. They're memory efficient to train. They demonstrate state-of-the-art performance. They're straightforward to implement with existing tools. And as we've also just seen, we can also use them as a way of training flexible, general, state-of-the-art SDE models. And so very broadly, as we saw at the start, neural differential equations are a direct extension of everything that's already going on in mathematical modeling. And so as a result of that, I think really our biggest challenge at this point is just that we need to convince the rest of the world that they should be using these things too, and that they can profitably use these things to build on top of and really extend the same techniques that are already ubiquitous throughout mathematical modeling. So these are the three papers I've really been discussing today. The first one is the original neural CDEs paper. Then we've got another one on the long time series. And then we've got a third one specifically regarding neural SDEs. And I think you've all got the slides, so you can look those up. So as I said, a version of these slides is also available on my website. Do feel free to send me an email or poke me on Twitter if any questions spring to mind later. I'm very happy to field questions. And I'm also a developer, or at least involved with most of the major PyTorch libraries. So I'm happy to talk about those too. And all that really remains to say is thank you very much for your attention, and I will take any questions.
All right. Well, thank you very much, Patrick. Questions?
Yeah, maybe just briefly more, just more a comment that, we within the Film Center, which is hosting your seminar, we also have quite a bit of software that, overlaps with, what you described. So, I mean, I can send you some more information if you're interested. So
certainly, I'm interested. What kind of framework do you use?
Well, it's probably, I mean, it's well, I'm referring to ADCME, the work that we're doing in my group. And I mean, we can talk offline. I mean, we use, we use TensorFlow as the backend. It's a Julia interface that allows you to write differential equations with neural networks embedded. And yeah, so I mean, definitely overlaps with what you're doing, but I mean, we can discuss the interface and how you did it. There might be some interesting discussions there.
Yeah, very happily.
Yeah, I'll
get in contact.
Put you in touch with my students. Yeah.
Thank you.
Hi, this is Leo. I have a short question. So I was wondering. So basically, really that you have like a differentiation on X, and what if the observation of X series is noisy? What will happen?
Two things, I guess. Either you can just push through all of this anyway, and it should basically just work, because as long as the noise is present in your train set, then your model just treats it as an input like any other, and it learns to trust things to the extent that it can. But also, if you in fact actually have some measure of how much noise there is, then just push that in as an additional input. Make that another channel.
I didn't get the second point. Could you please?
Sure. So if you actually know not just that something is noisy, but you know how noisy it is, you've got for some reason some measurement of this, then you can just add that as an additional channel, as an additional dimension to your data, to your capital X, to this path, because then you're also telling your model how much you're trusting the input, and the model can learn to interpret it correspondingly.
Oh, but my point is, so let's suppose like we have very dense observation on X, and the issue observation is pretty noisy. Will that noise just make everything make the DX this information totally broken?
I don't think it should be an issue. If you have any machine learning framework, the neural CDE or otherwise, as long as the noisiness in the data is the same in both train set and test set, then things work out. The model learns to respect the uncertainty in what it's given.
Oh, yeah. Okay, got it. Yeah, thank you.
I have a couple of questions, maybe. So for the case of stochastic differential equations, now that this path that you have would be the path of a Brownian motion, right? So that one is not differentiable.
Yes.
However, there, are you going, because you're sampling this Brownian motion, are you going also to interpolate it?
Okay, so yes and no is the answer. If you want, yes, you can take your SDE, you can sample it, you can do your interpolation and sort of just kind of push through exactly as I've described. If you want to, you can completely also do this in continuous time. And in that case, then you're correct. You can't use this differentiation interpretation. And you actually sort of have to fall back to kind of normal CD SDE theory. That's just, mildly more complicated.
Okay, so is this where the rough path theory will come in order to describe somehow the properties of these paths?
If you want it to, yes.
Okay, because I mean, I came to this through the rough path theory.
Oh, did you?
Yeah, I mean, I looked at it, and my understanding was that the rough path theory somehow through this signature, it allows you to go into the heart of what a time series is, meaning it uses these extra quantities to extract information about the time series, right? And that's why I'm asking that it was built by your supervisor, right? In order to deal with paths that are, well, with series that are not smooth. So for the case of a Brownian motion, would you need, in order to make your theory, to prove things about for what you're doing, would you need to go into into rough path theory in order to prove stuff?
No is the answer.
Okay.
I think if you sort of already understand the theory and have the theory, then it's like a great way to look at things. But for example, the equations that I've just put back up, this green and yellow stuff at the very top,
yes,
you can interpret all of this just in terms of normal SDE theory, if you wish.
Okay. All right. So, and in your, okay, but when you use that, for your SDE case, don't you need to do some kind of interpolation in your code? I mean,
no. So
Okay.
what I've got here, this whole combined set of equations, you can actually put them all together into like one really big drift function, one really big diffusion function, and solve this whole thing forwards as one big SDE.
Okay. All right. I see. Okay. So have you tried to recover, for example, for this Heston model, did you try to recover by using this formulation something that would resemble what is in the actual model?
So but the short answer is no, and there's a reason for it.
Okay.
And so I mean, certainly if you wanted to, you could generate data from a Heston model and fit a neural SDE to it. But because your neural SDE is a neural network, then there's kind of no way to look at your neural network and say, oh yes, my value for kappa should have been whatever. Right?
No. I meant to actually get a functional form. In other words, do you really need very complicated networks, neural networks, in order to capture the dynamics of this 2D model?
Oh, I see.
Yes.
So in theory, no, because in theory, this is very simple. And there exists a simple neural network doing the job.
Okay.
In practice, it's a general rule in machine learning that you want your neural networks to be too complicated for what you're trying to model, because they train better that way.
Right. So my question was how big they should be in order to be able to recover the dynamics of such a model.
So as I say, I've not tried the Heston model specifically, so exactly I'm not sure, but they generally don't need to be very big. You hear a lot of sort of applications of neural networks where they're sort of terrifyingly large with billions of parameters. But here you could be looking at widths of, sort of 64, 128, something like that. That'll probably do the job quite happily.
Yeah, it will be interesting to see when you go into a large dimensional SD system, what kind of neural networks you will actually need there in order to do this training. But it's an interesting idea. I like it. It's just that I'm thinking, further down the road, when going from this slide to the actual implementation.
Yeah, I mean, at the end of the day, this is something which can reasonably straightforwardly be solved just by picking a big enough neural network and train it on a big enough computer.
Yes,
and that does just work. That's what we've been doing.
Right. Of course. Okay. Any other questions?
Hello, this is Kyle from Stanford. I have a question with regard to your explicit scheme. You mentioned that you use explicit scheme to evolve this XT or HT, right? So for this kind of a scheme, if you use explicit scheme and you have no constraint on your neural network, will you have some problem like a stability or something like that? For example, if your step set is too large, and
So the answer to that is yes and no. It is yes, in the sense that if you really want to approximate your differential equation, then yeah, maybe you need to think carefully about what your differential equation solver is doing. And maybe you take small step sizes, maybe you want to use an implicit scheme, et cetera, et cetera, et cetera. Your differential equation solver is, I don't know, maybe taking fixed steps, then you can actually use, like the learning can actually learn to respect those fixed steps. And what actually ends up being fitted to data isn't the continuous limit of the SDE, but actually your discretization that you're actually using. And the model, as a result, just work despite that. Does that make sense?
Actually, I'm confused. So you have a ground truth model, right? And you want to approximate that ground truth. So if you use step sets that are too large, and how can you approximate your true model? Yeah, because for true model, if you use larger step sets, you get a divergence for your numerical schemes, right?
So when you say true model, are you describing some already learned neural SDE, for example, that you now want to evaluate?
No. I mean you have a ground truth, right?
Yes.
Yeah, and for that ground truth, your steps, if you use a very large step size, you might get a divergence, right? But you desire to approximate your ground truth using a neural network, but you fix the step size, and you do not know whether your step size is too large or too small.
It depends how much you want your model to really meaningfully be an SDE. So obviously this is kind of how you present it, and I think it kind of looks very nice and pretty this way. And if that's the case, then yes, use small step sizes or something. But as long as if you pick some sort of medium or larger step size, then the model you're fitting is arguably not an SDE, but some discrete approximation to an SDE. And now you fit your discrete approximation to an SDE to your data. And that's still a model, right? That still can be fitted to data. I could still do a perfectly good job.
Okay.
It's just not an SDE. It's a discrete approximation to one.
Oh, so all you want is to fit your data, right?
If that's all you care about, then yeah, you can just do that.
Right. I think that what Kyla is asking is that since you're learning, like you said, if you take a large step size, you're learning a discrete approximation. This generator, what we'll learn in essence, is another numerical integrator. It will learn a numerical method of how to take a noise input and produce a path, right, which is the output.
Sure.
And the question I think that Kyla had was whether there is a limit as to how coarse you can take your time step before this numerical integrator that you're learning through the generator becomes unstable.
Right. So I think the answer is yes. There's been a couple of recent papers showing this in the ODE case, that you sort of hit some kind of point at which the discretization really starts mattering.
And it should, because these are explicit methods, right? So at some point, there has to be a stability constraint.
Yeah, I mean, you don't have to use, your sort of Euler midpoint Runge-Kutta whatever method. If you by all means, it's, for example, for ODs, for all means use an adaptive step size, Dorman Prince, whatever you like. That will work.
Right.
Okay, thank you.
Any other questions for Patrick?
Hi, Patrick. This is Jen.
Hello.
Hi. So can I ask a question about the neural CDE model? Basically, I think that model is pretty much like, as you mentioned, is pretty much like an RNN. But like in general, for a discrete RNN model, people normally face things like vanishing or exploding gradients. But for the CDE model you introduced, you say that you can learn a very long time series. So I'm wondering, like, how can you solve that problem, like explicitly or implicitly?
Yeah, so these are the slides I really skipped over. And the answer is two things, basically. One of them is just a simple trick, basically, to your neural network architecture. If you look at sort of standard RNNs, then the two most popular models are really GRUs and LSTMs. And the reason those are the most popular is because they have things like gating procedures, which fundamentally what they're doing is constraining the rate of change of hidden state. That's what stops things from exploding too crazily. I mean, arguably, there's still like a theoretical Lyapunov, et cetera, theory going on there, which says that ultimately things go wrong. But for practically sized problems, constraining the rate of change of hidden state will usually fix things. And you can do the same thing here. You pick a neural network which constrains the rate of change of hidden state. That's part one. Part 2 is where you can actually really use CD theory and the sort of the signatures and log signatures that have sort of briefly been mentioned but not really discussed. You can use that to do sort of clever transforms of your input time series, so that it goes from being a long time series to a short time series, but still has interesting information. But that's technical. If you're really curious about long time series, then this is the second paper here.
Yeah. Okay. Yeah. Maybe I should check that like later.
Mm-hmm.
Thank you.
Jen, I gave you I sent you the PowerPoint of Patrick.
Oh, okay. Thank you.
Yeah. So I sent you the PDF. But Patrick, I wanted to thank you for giving an excellent talk and be patient. We are a rowdy group, and we would like to be rowdy, and I want to encourage everybody to be very rowdy. Don't take it personally. This is how we learn. That's why I wanted to make sure that there's lots of questions. I just want to tell you that a few years ago, not too many, we invited Terry Lyons at Brown, and he gave a series of lectures and so on. And I realized actually he's an excellent C++ programmer. So, so every time I take him out to lunch or dinner, we would end up talking about C++. So I was wondering if he updated his programming skills to Python now. Julia.
To my knowledge, no, and that's where I start coming in. I'm the Python guy in the group.
Yeah. That's an excellent talk. I think that's thanks, Panos. Thanks for inviting Patrick. That was a great idea, and I encourage everyone to invite people here. But I just wanted to say that look, we're a kind of civilized group. We have to ask questions, and at some point we'll stop asking questions. But I think it's that's I never learned anything from these very formal talks that nobody talks and just monologue, and that's so I want to keep this informal, this group, and I understand Nat's point and so on, but I want to make sure that everybody can ask questions, especially the students and everyone. So that's why
not at all. It's honestly very flattering.
Actually, yeah, I mean, they are interested. I can tell you. In other talks, they don't ask questions, but they were interested a lot in your talk. So that was great. Yeah. Panos, I think you are closing. Okay. You are the master of ceremony.
All right. Well, if there are no more questions then for Patrick, well, thank you again, Patrick. I think you deserve to rest now. It's past 11 p.m. where you are, right?
11:20.
11:20. All right. So thanks, everybody. And we'll meet again at the next webinar.
And thank you very much for hosting
Next Monday we have Ken Golden, who wrote a recent SciAmp paper on ice modeling, the real expeditions. Ken is a great speaker, so please tune in.
So please, everyone, come back next week. Thanks again, Patrick.
No problem at all. Thank you very much for having me.
Thank you. Thank you.
All right. Take care. Bye-bye.
Bye.